Chapter 4 Steady State Heat Transfer. We are normally interested in how long it takes for the hot coffee in thermos to cool a certain temperature, which cannot be determined from a thermodynamic analysis alone. Heat and other forms of energy. Microscopic energy. The forms of energy related to the molecular structure of a system and the degree of the molecular activity. Internal energy. The sum of all microscopic forms of energy. Sensible heat. Internal energy associated with the kinetic energy of the molecules. Latent heat. Internal energy associated with the phase change of a system. Chemical energy, bond energy. Internal energy associated with atomic bonds in a molecule. Nuclear energy. Internal energy associated with the bonds within the nucleus of the atom itself. Enthalpy. On a unit mass basis. Heat flows in the direction of decreasing temperature. What is heat transfer? Thermal energy is related to the temperature of matter. For a given material and mass, the higher the temperature, the greater its thermal energy. Heat transfer is the study of the exchange of thermal energy through a body or between bodies which occurs when there is a temperature difference. When two bodies are at different temperatures, thermal energy transfers from one with higher temperature to the one with lower temperature. Heat always transfers from hot to cold. Table 1 shows the common SI and English units and conversion factors used for heat and heat transfer rates. Heat is typically given the symbol Q and is expressed in joules in SI units. The rate of heat transfer is measured in watts, equal to joules per second, and denoted by Q. The heat flux, or the rate of heat transfer per unit area, is measured in watts per area and uses Q for the symbol. Making an unsteady state heat balance for the x direction only on the element of volume or control volume in figure 4.1 by using equations 4.1 and 4.2 with the cross-sectional area being A square meters, where Q is rate of heat generated per unit volume, assuming no heat generation and also assuming steady state heat transfer where the rate of accumulation is 0. This means the rate of heat input by conduction, the rate of heat output by conduction, or Qx, is a constant with time for steady state heat transfer. Introduction to steady state heat transfer. The transfer of energy in the form of heat occurs in many chemical and other types of processes. Heat transfer often occurs in combinations with other unit operations, such as drying of lumber or foods, alcohol distillation, burning of fuel, and evaporation. The heat transfer occurs because of a temperature difference, driving force, and heat flows from the high to low temperature region. In section 2.3, we derived an equation for a general property balance of momentum, thermal energy, or mass at unsteady state by writing equation 2.3. Writing a similar equation, but specifically for heat transfer. Assuming the rate of transfer of heat occurs only by conduction, we can rewrite with Fourier's law. Conduction. In conduction, heat can be conducted through solids, liquids, and gases. In solids, atoms are bound to each other by series of bonds analogous to springs as shown in figure 1.1. Three modes of heat transfer. There are three modes of heat transfer: conduction, convection, and radiation. Any energy exchange between bodies occurs through one of these modes or combinations of them. Conduction is the transfer of heat through solids or stationary fluids. Convection uses the movement of fluids to transfer heat. Radiation does not require a medium for transferring heat. This mode uses the electromagnetic radiation emitted by an object of exchanging heat. When there is a temperature difference in the solid, the hot side of the solid experiences more vigorous atomic movements. The vibrations are transmitted through the springs to cooler the sides of the solid. Eventually, they reach an equilibrium where all the atoms are vibrating with the same energy. The heat is conducted by the transfer of the energy of motion between adjacent molecules. Example of heat transfer mainly by conduction are heat transfer through walls of exchangers or a refrigerator, freezing of the ground during the winter, and so on. Convection. Forced convection heat transfer. Fluid is forced to flow past a solid surface by a pump, fan, or other mechanical means. Natural convection heat transfer. Warmer or cooler fluid next to the solid surface causes a circulation because of a density difference resulting from the temperature differences in the fluid. Convection. The transfer of heat by convection implies the transfer of heat by bulk transport and mixing of macroscopic elements of warmer portions with cooler portions of a gas or a liquid. It also often involves the energy exchange between solid surface and a fluid. Natural convection, or a free convection, refers to a case where the fluid movement is created by the warm fluid itself. The density of fluid decreases as it is heated. Thus, hot fluids are lighter than cool fluids. Warm fluid surrounding a hot object rises and is replaced by cooler fluid. The result is a circulation of air above the warm surface, as shown in figure 1.4. Conduction. In conduction, heat can be conducted through solids, liquids, and gases. In solids, atoms are bound to each other by a series of bonds analogous to springs as shown in figure 1.1. Convection coefficient H is the measure of how effectively a fluid transfers heat by convection. It is measured in W divides meter square K and is determined by factors such as the fluid density, viscosity, and velocity. Wind blowing at 5 mph has a lower H than wind at the same temperature blowing at 30 mph. The rate of heat transfer of a surface by convection is given by Q convection equals H A T surface minus T infinite, where A is the surface area of the object, T surface is the surface temperature, and T infinite is the ambient or fluid temperature. Forced convection uses an external means of producing fluid movement. Forced convection is what makes a windy winter day feels much colder than a calm day with the same temperature. The heat loss from your body is increased due to the constant replenishment of cold air by the wind. Natural wind and fans are the two most common sources of forced convection. Radiation. Radiation is the transfer of energy through space by means of electromagnetic waves in much the same way as electromagnetic light waves transfer light. Radiation differs from heat transfer by conduction and convection in that no physical medium is needed for its propagation. All three main types of rate transfer processes, momentum transfer, heat transfer, and mass transfer, are characterized by the same general types of equation. The minus sign in equation 4.1 is required because if the heat flow is positive in the given direction, the temperature decreases in this direction. Fourier's law of heat conduction. The transfer of heat by conduction also follows this basic equation and is written as Fourier's law for heat conduction in fluid or solids. The units in equation 4.1 may also be expressed in CGS system with Qx in calorie per second. A is centimeter square, K in calorie per second, Celsius, centimeter, T in degrees Celsius, and X in centimeters. In English system, Qx is the British thermal unit per H, A in feet square, T in degrees Fahrenheit, X in feet, K in British thermal unit divide to H degrees Fahrenheit feet, and Qx per A in British thermal unit A per H feet square. From Appendix 8.1, The conversion factors are for thermal conductivity, for heat flux and power. Fourier's law can be integrated for the case of steady-state heat transfer through a flat wall of constant cross-sectional area A, where the inside temperature at point 1 is T1 and T2 at point 2, a distance of x2 minus x1 meter away. Rearranging equation 4.1 is integrating, assuming that K is constant and does not vary with temperature, and dropping the subject X on Qx for convenience. The rate of heat conduction through a solid is directly proportional to its thermal conductivity. Heat loss through an insulating wall. Calculate the heat loss per meter square of surface area for an insulating wall composed of 25.4 millimeter thick fiber insulating board, where the inside temperature is 352.7 K and the outside temperature is 297.1 K. Solution. From Appendix A.3, the thermal conductivity of fiber insulating board is 0.048 watt per meter K. The thickness x2 minus x1 is 0.0254 meter, substituting into equation 4.1. 10. Thermal conductivity. The effectiveness by which heat is transferred through a material is measured by the thermal conductivity K. A good conductor, such as copper, has a high conductivity. A poor conductor or an insulator has a low conductivity. Conductivity is measured in watts per meter per Kelvin. Solids. The thermal conductivity of homogeneous solids varies quite widely, as may be seen for some typical values in Table 4.1. The metallic solids of copper and aluminum have very high thermal conductivities, and some insulating non-metallic materials such as rock wool or corkboard have very low conductivities. Ice has a thermal conductivity much greater than water. Hence, the thermal conductivities of frozen foods such as lean beef and salmon given in Table 4.1 are much higher than for unfrozen foods. Thermal conductivity. In Table 4.1, thermal conductivities are given for a few materials for the purpose of comparison. More detailed data are given in Appendix A.3 for inorganic and organic materials and 8.4 for food and biological materials. As seen in Table 4.1, gases have quite low values of thermal conductivity, liquids intermediate values, and solid metals very high values. Gases, the thermal conductivity increases approximately as the square root of the absolute temperature and is independent of pressure up to few atmospheres. At very low pressures, however, the thermal conductivity approaches zero. Liquids. The thermal conductivity of liquids varies moderately with temperature and often can be expressed as linear variation. Where A and B are empirical constants, thermal conductivities of liquids are essentially independent of pressure. Convective heat transfer coefficient. It is well known that a hot piece of material will cool faster when air is blown or forced by the object. When the fluid outside the solid surface is in force or natural convective motion, we express the rate of heat transfer from the solid to fluid, or vice versa, by following equation. Q equals HA T surface minus T fluid, where Q is the heat transfer rate in watts, A is the area in square meters, TW is the temperature of the solid surface in K, TF is the average or bulk temperature of the fluid following by in K, and H is the convective heat transfer coefficient in watt per square meters per K. In English units, H is in British thermal units per H per square feet per degrees Fahrenheit. The coefficient H is a function of the system geometry, fluid properties, flow velocity, and temperature difference. In many cases, empirical correlations are available to predict this coefficient, since it often cannot be predicted theoretically. Since we know that when a fluid flows by a surface, there is a thin, almost stationary layer or film of fluid adjacent to the wall, which presents most of the resistance of heat transfer. We often call the coefficient H a film coefficient.